Hello and welcome everyone to the first virtual training module hosted by the Sustainable Materials Management and Extreme Events Reconnaissance Organization. This training module will focus on post-disaster waste materials estimation, integrating US EPA's iWaste tool. My name is Dr. Derek Mannheim, and I'm a researcher within the SUMMEER organization who will be leading this first training module today. I have prepared a brief presentation and an in-depth case study tutorial to walk you through the basic steps of using iWaste to make reliable predictions of post-disaster waste materials quantity and composition. These initial estimates are necessary to comprehend and explore the efficacy of various sustainable materials management and treatment options for post-disaster waste materials following a natural disaster event. A major contribution of the SUMMEER organization is the preparation of a virtual assessment report that summarizes key findings related to the current management of post-disaster waste materials in the wake of a catastrophic natural disaster. Within each virtual assessment report, formal estimation and reporting of the material quantity and composition is necessary to provide a quantitative understanding of the amount and types of waste generated after a natural disaster. This data provides a baseline understanding of the sustainable waste management options that could be implemented and allows a direct comparison to field reported data. As with any modeling tool, there is inherent uncertainty to address with these modeling predictions. Effectively characterizing this uncertainty requires a combination of predictive modeling approaches, such as the use of iWaste and HAZUS-MH to arrive at a range in waste material characterization estimates. So as a brief introduction, iWaste is an easy to implement modeling tool for generating order of magnitude, weight, volume, and composition estimates of post-disaster waste materials following a disaster. HAZUS-MH is a much more complex and powerful state-of-the-art risk assessment software program developed and maintained by FEMA for analyzing potential losses from floods, hurricanes, earthquakes, and tsunamis. Together, these tools can provide both lower and upper predictive uncertainty bounds for the debris characteristics following disaster, including, for example, the weight, composition, and/or the spatial location. This training module presents a standardized and refined framework for post-disaster waste materials estimation integrating US EPA's iWaste tool. The intended audience of this training module is for new members participating in virtual assessment report activities that need to get up to speed with available debris estimation software and for the greater research community. After viewing this module, you will gain new experience with the capabilities that iWaste offers, along with a general understanding and awareness of how to best generate, analyze, and post-process results using iWaste with a specific emphasis on the development and publication of future virtual assessment reports. And now I'll present a brief introduction to iWaste. The acronym iWaste stands for Incident Waste Decision Support Tool. As part of an all hazards planning framework, this tool was initially developed and maintained by the US EPA for responding to chemical, rheological, and biological events, and for managing contaminated debris streams. However, iWaste is also applicable to a diverse range of natural disaster events, as shown in the figure here, which is the focus of this particular training module. For example, iWaste can be applied to estimate debris characteristics from earthquakes, wildfires, floods, hurricanes, as well as tornadoes. Currently, iWaste is freely available as an open access, web-based tool. The web address is included in the presentation here so that you can actually access it during the tutorial portion of the training module. iWaste is a great tool for generating order of magnitude and approximate weight, volume, and composition estimates of post-disaster waste materials following a natural disaster event. iWaste contains three main user interfaces that I will review in detail during this training module. The first interface is the Waste Materials Estimation Tool, or WME, that is used to obtain the actual predictions of waste quantities and composition. The second interface is the Facility Databases Tool, which allows the user to actually query and identify the location and characteristics of existing waste management infrastructure, including recycling and recovery centers, solid waste landfills, waste combustion facilities, and other management operations. The third interface is a repository of important guidance information to assist researchers with identifying relevant federal, state, and community-specific regulatory requirements for managing post-disaster waste materials. The Waste Materials Estimator is the primary tool we'll be using within the greater iWaste framework for making predictions of post-disaster waste materials quantity and composition. Please note that it is a generalized worst-case scenario approach to debris estimation and that it assumes complete destruction of the disaster-affected area. It is thus considered a disaster-independent approach, as it does not take into account the specific physical attributes of the disaster event, such as the flooding depth, the wind speed, or other important properties that influence the extent of building damage. However, the main strengths of the WME tool within iWaste is that it can generate the total structural, non-structural, or interior and open area material, such as soil, vegetation, or asphalt, mass and volume quantities for a disaster-affected region of interest. The focus of this training module is to show you how predictions can be tailored to represent a disaster event of interest and to enhance the reliability of predictions to better reflect field collected data. To run the WME tool within iWaste, the user will need to specify a few important inputs, as observed in the figure to the right. These inputs include the total affected area, square miles, the number of movie theaters, hospitals, single-family homes, hotels, offices, primary schools, and shopping malls. Importantly, the building occupancy classes delineated by the WME tool are consistent with HAZUS MH, as shown in the parentheses on this slide here. For some inputs, the number of small, medium, and large buildings are necessary to define. The definition of what constitutes either a small, medium, or large-sized building can be accessed within the WME tool by clicking on the blue heading for each building occupancy class. One of the most difficult steps to running iWaste is to specify the necessary input parameters. If the input parameters are entered incorrectly for a given disaster event, then the reliability of predictions will be significantly affected. Therefore, to better constrain the WME simulations and improve the reliability of the results, the comprehensive data management tool available from HAZUS MH must be consulted to obtain estimates of the number of buildings within each occupancy class. Prior to initiating WME predictions, I will suggest running HAZUS MH simulations for the disaster event of interest to ascertain the specific building stock attributes within the disaster-affected region. To set up, run, and summarize the results from HAZUS MH, please refer to the companion training module focusing specifically on HAZUS MH. After running a successful HAZUS MH simulation, you will need to identify the census blocks that experience some extent of damage to the general building stock. This is a critical step, as iWaste will assume that all the buildings specified in the inventory as input to run the tool will be completely destroyed in the wake of the disaster. Therefore, a conservative damage level threshold identified from previous research is to consider only the buildings with damage greater than 1% from HAZUS MH simulation results. Then, using the CDMS tool, you'll be able to query the specific area and number of structures that are present in the disaster-affected region. This information should be summarized and used as input to obtain more realistic simulations within iWaste that are significantly more comparable to field data. I will review how to set up and use the CDMS tool during the case study tutorial presented at the end of this presentation. After obtaining the refined inputs to the WME tool, now you're ready to run WME and summarize the results. When you run WME using the online tool, the results will be displayed in both graphical and tabulated formats. The graphical outputs are shown here as an example using results summarized by weight in US tons. The bar charts depict the total tonnage of each waste material as a function of the building occupancy class. As observed in the figure, soil and vegetative debris dominate the total material generated for this disaster event. Tabulated results are also presented for each type of waste or material category shown in the figure, which can be accessed from the online results presented from the WME tool. After running each simulation, it is very critical to download and save the data in Excel using the download option. The graphical outputs shown in this figure are an example of the results summarized in volume in terms of cubic yards. The bar charts now depict the total volume of each waste material as a function of the building occupancy class. Similar to the previous figure, soil and vegetative debris dominate the total material quantities generated for this simulated disaster event on a volumetric basis. Once you have plotted and tabulated the WME results, the next step is to take some time to review the major assumptions and parameters applied to generate the predictions of waste quantities. Ask yourself the important question of whether these predictions seem reasonable. In this reasonableness check, the first item to review is the Estimate Criteria tab that summarizes the general details behind the assumptions used to estimate the quantity of waste material generated. Of the waste material to be most judicious with during this critical review is the open space category. From the Estimate Criteria tab, the major parameters identified for the open space category are the percentage of open space versus building infrastructure, along with the percentage of vegetation, the soil, asphalt, and concrete, as well as the depths of these materials used in the simulation, along with the densities of each material. The preset densities that are used in iWaste for vegetation, soil, asphalt, and concrete materials are 75, 1,521, 819, and 2,600 kilograms per meters cubed, respectively. Of the major parameters that are identified, only the percentage of open space can be computed using the data obtained from CDMS by comparing the total building to the total area per census block. The remaining parameters cannot be estimated nor informed from the details provided in CDMS. However, they can be calculated using the National Land Cover database available from USGS, if more reliable simulation results are in fact desired. In addition to the Estimate Criteria tab, the waste material category links, highlighted in blue, can be selected to understand what material densities are used in the calculations. For example, the standard density applied for vegetative materials is 0.065 tons per cubic yard, which corresponds to 75 kilograms per meter cubed. This has been updated from 4 tons per cubic yard used in previous iWaste versions. In addition to the bulk density of the vegetative materials, a standard land cover vegetation density is assumed in iWaste. According to FEMA, for an average 1 acre area in the US, approximately 16,000 cubic yards of vegetation are present and contribute to the debris generation following a disaster event. Note that the more advanced user cannot update these factors manually if more site-specific estimates of vegetative debris are desired, as they are hard-coded into the WME tool. In addition to this validity check, it is often helpful to construct supplementary figures or tables outside of iWaste that assist in the presentation and interpretation of the debris estimation results. Using the Excel data that was generated, for example, plots can be generated in MATLAB or Python that compare iWaste predictions for various regions of interest. For example, I have shown here some results comparing iWaste simulations for 2 regions affected by the Michigan flooding event in 2019. For more reference, please consult the published report summarized on the SUMMEER website. The link is provided on the slide here. The first plot compares the total post-disaster waste materials estimation as a function of the waste material category. For both regions, the open debris is significant, along with structural debris components. Of the interior building components, furniture is associated with the largest debris tonnage. The pie chart shown here demonstrates the differences in material composition as a function of open debris in panel A, structural debris in panel B, non-structural debris panel C, electronics D, and E, furniture between the 2 different regions. As you can see, the material compositions within each of these subclasses for each of these 2 regions were relatively similar when comparing the overall iWaste predictions. Following the WME interface, the next step will be to identify potential treatment and disposal facilities in the disaster-affected region. The second tab available within iWaste is the Facility Database Query tool that can locate a number of waste treatment facilities in the disaster-affected area. Facilities relevant to the SUMMEER applications might include industrial, MSW, and CND waste landfills, along with combustion and recycling recovery facilities. Within the recycling recovery facilities, the user can select from a variety of classifications, including metals, tires, or electronic-specific facilities. In addition, other waste management facilities, such as wastewater treatment operations, hazardous waste landfills, or decontamination centers can also be searched if dealing with hazardous liquid or solid streams. When performing the facility identification step, it will be necessary to specify the radius of influence or ROI, that is feasible for managing the post-disaster waste materials. The ROI can be approximated based on the severity of the disaster event. Disaster events that are less severe will result in fewer disturbances to the roadways and bridges and will enable more practical or economical transportation of waste materials to facilities located farther away from the disaster focal point. For the upper limit, approximately 20 miles is used considering the large quantities and densities of generated materials. When dealing with more severe disaster events, a smaller ROI is recommended, where a lower threshold of 5 miles has been suggested based on previous data presented in our collection of published virtual assessment reports. Please note that these are suggested guidelines and are not truly definitive estimates of waste hauling distances that are practical for waste management. Once the ROI has been specified, key characteristics of these facilities are required, including the facility classification, for example, a landfill, recycling, and recovery center, etc., the number of facilities and geospatial location, distance from the focal point of the disaster event, potential waste accepted, and the capacity of the facility. Most of these characteristics can be researched using the query tool available in iWaste, such as the facility classification, number of facilities, and waste accepted. Additional information, such as the capacity and distance to the focal point of the disaster event, can be researched from the disaster debris recovery tool available from US EPA and or calculated using ArcGIS. The last interface that can be explored in iWaste is the Relevant Guidance Information tab, which provides useful information about the regulatory requirements and general disaster waste management policies on the federal, state, and local levels. Using this interface, you can query various case studies, fact sheets, regulations or guidance documents, planning documents, and important information for pricing debris management equipment that will be useful in generating the virtual assessment reports. Here I have shown some important information related to the recycling guidance provided by US EPA, as shown in this tab to the right. Note that other tabs can also be selected and queried under the natural disaster list presented on the website. Now I will walk through a case study tutorial using the Midland, Michigan flooding event as an example application of iWaste and the CDMS tool available within HAZUS MH. Please recall that using the CDMS tool and corresponding census tract damage level results from HAZUS simulations are critical prerequisites to properly define the building inventory inputs in iWaste. Again, you can refer to the companion training module focusing on HAZUS MH to review how to set up, run, and analyze the debris generation results for a flooding event. This particular disaster event was caused by a historic rainfall in the central Michigan region, which was exacerbated by a succession of dam failures and breaches, resulting in catastrophic inundation and damage to both urban and rural areas located downstream. The flooding damage was centralized among two particular urban locations, the city of Midland and Saginaw. In this virtual assessment report, both iWaste and HAZUS MH simulations were conducted to ascertain post-disaster waste material quantities and composition. These simulation results assisted in the identification of available pathways for recycling and reuse, potential contamination of the debris streams, along with a detailed assessment of the adequacy of local waste management infrastructure for handling the debris generated from this event. In this short tutorial, we'll start with defining the inputs to the WMU tool within iWaste using CDMS from HAZUS MH. I will then review how to input this data and run a single iWaste simulation. I will then review how to use the facility database query tool, which will demonstrate how to locate landfills as well as other recycling and recovery facilities in the region. To start the tutorial off, I will open the CDMS tool and load in the statewide dataset within the Comprehensive Data Management System tool available within HAZUS MH. Before using the tool, make sure you load in the statewide dataset for your state of interest. And to do this, you'll have to download the statewide dataset as a .exe file from the FEMA repository available online. Place this .exe file in the correct folder on your computer, and then extract all of the files by running the .exe application. After you have done this, go to Tools, specify HAZUS MH data location, and here you will specify the path to the directory where you have placed this .exe file. So when you extract all of the contents, you'll come up with the MDF file. So that MDF file is what you want the CDMS tool to locate. So here I have it sent to my C drive, HAZUS data inventory, and Michigan, indicating the Michigan data set. So I'll close this. And if you have done this correctly, you will see that your current state shows up in the box on the left-hand side here. So once we have correctly loaded in the data set, we'll now go to the Query Export Statewide Datasets tab. And that's already selected here. The next step is to search by geographic area. So we'll go down to a statewide level, or the county level here, and then select, in this case, we are interested in Midland County for the flooding event. So we'll go down to Midland and hit the right arrow to indicate we have selected the county of Midland. And then we'll go down to search by data layer and then go under this tab here to find aggregated data. So what we're interested in is the building counts by census block, as well as the building square footage by census block. So we'll highlight both of those and click the right arrow. Make sure we have those selected data layers on the right here. Don't worry about selecting the hazards here, and then click search. All right, so these are the search results returned by the CDMS tool. You'll see here that we have the census blocks as each row within the table, and then going across in each column, we have each of the individual occupancy class categories. So remember, we're in HAZUS MH, we're dealing with, or in iWaste, we're dealing with 7 individual building occupancy classes. That was indicated earlier on in this presentation. So we'll actually, once we have exported this data for both building counts and square footage, we'll then try to filter these results by those 7 individual building occupancy classes. So again, when you are ready to export the results, just hit the Export to Excel tab, and then you should be good to go with the next steps performing the HAZUS simulations. And now I'll walk you through how to filter the data by building damage level in HAZUS MH. Once you have conducted a successful HAZUS MH simulation, you'll be able to identify and filter the individual census blocks that have experienced greater than 1% damage levels. As a review, 1% damage level threshold indicates that at least 1% of the general building stock in the affected region was classified as above the undamaged state, or into one of the 4 damage-associated states. Remember that there are 5 overall damage levels used by HAZUS MH, including undamaged, minor, moderate damage, severe damage, and destroyed. Note that if a higher damage level threshold is used, iWaste simulation results will be further constrained in terms of the quantity of debris generated. Therefore, a lower value is usually more conservative in that there is a significant uncertainty associated with the damage states predicted by HAZUS. Please note also that you only will be able to perform a HAZUS MH simulation for an earthquake, flood, hurricane, or tsunami type disaster event. In the case of a wildfire or tornado, you will have to research the building damage extent online. For a wildfire event, usually detailed geospatial information is available from a state fire agency within 1 to 2 months of the event occurrence that summarizes the damage extent information obtained from field observations, as shown in this slide here. For the Camp Fire events in California, this was obtained from CAL FIRE data, where it now shows the destroyed structures in red, major, minor, and affected structures in orange, yellow, and green, and then no visible damage in black. So once you have this data in ArcGIS, you can overlay this geospatial information onto the census block map data provided in HAZUS to ascertain which census blocks have experienced greater than 1% damage. A similar approach can be taken for tornado type events, where a significant amount of data can be obtained from STEER, Structural Extreme Events Reconnaissance Group, from their own field reports available from their reconnaissance missions within Design Safe, as shown here. And again, I've labeled that destroyed structures in red, severe, moderate, minor, in orange, yellow, and green, and then undamaged in blue. And you can see how it is, the damage state is related to the overall tornado path. This was for the Linwood tornado in Kansas in 2019. Now I'll show you how to obtain the damage level information from HAZUS MH. So on this screen, we are working within HAZUS MH. We have already run a successful simulation. We would like to access the damage state results. To access these results, we'll go to the Results tab at the top here and go down to General Building Stock, and then select Building Damage States, and then by occupancy. All right, and here we have a table that pops up that shows all the census tracts again in rows, and then you have each of the 5 damage level classifications in columns across the table. So make sure when you export these results that all occupancies are selected here. That eases the analysis of the data overall. And note that you can also filter by the 7 specific occupancy classes we are interested in for conducting the I-Way simulations, but the overall filtering of the results becomes a little bit more complex and difficult. So we'll stick in most of the cases using all occupancy classes. You can then highlight all the results by selecting each of the columns, and then right-click, and then hit Export Data. Then you'll select CSV file type and hit Desktop. And you can name your file to whatever name is appropriate. And then all this tabulated data will be exported to a CSV file, and we can now work with it in Excel. All right, so now we have opened this exported CSV file in Microsoft Excel. And the next step is to isolate individual census blocks with damage greater than the 1% threshold. So to do this, we'll go over to the no damage column and then set up a filter here, as seen here under sort and filter. And then we'll go down, click the down arrow here, and then select number filters, and then go to less than or equal to 0.99. This indicates that the building damage within a given census block is greater than 1%. So once we do that, we can see that now we have filtered a great number of census blocks that are within this greater than 1% over that threshold. And now we are then ready to further process the results. Here are the results for the Midland, Michigan flooding event using this filtering approach. I'll now explain some of the more finer details for obtaining the necessary inputs to iWaste.
I've filtered out 2,677 census blocks from over 15,000 census blocks in Midland County that have actually exceeded this damage threshold here. And again, I have the census blocks as rows, and we have the individual occupancy classes as columns. After filtering the results, you'll need to sum all columns corresponding to a relevant building occupancy class in iWaste. Remember those 7 different classes for both the number of buildings and the building area. The total census area by the block, including the built and the non-developed area, can actually be attained directly from HAZUS MH simulations within the program. So you don't need to use CDMS to locate the total area of each block. So here in this sheet, I have summarized the total block area, including buildings and open areas, as you can see in square miles here. And again, that has been filtered by that damage threshold as well. So based on that, you can summarize the number of buildings, the total effective area, and the percentage of open area using these summary values, as shown in the following table here. So you can see in this table for Midland County, we have the total open space affected. We have the number of offices, schools, hospitals, shopping malls, hotels, single family residences, movie theaters. And notice that we used a number of buildings for small, medium, and large type buildings, because within HAZUS MH it's very difficult to further delineate each of these structures into either small, medium, or large type classifications as IOWAST classifies things. So to make things more simple, we just assumed equal distribution and apportionment of these different size classes. So in this case, we just said there's an equal number of small buildings, equal number of medium and large buildings there. So that's kind of where those values came from in terms of the overall inputs to the waste materials estimator in iWaste. So I will now enter these inputs into the WME tool and run the simulations online. So as you can see here, we have iWaste already open up. Here we have the materials estimator tool, again, already available here. So we'll put in, again, our updated open space value. We have the movie theaters, single family residences, hospitals, and again, by size distributions as well. And in addition to that, for my calculations, comparing the building area to the total area per census block, the percent open space is on the order of 99%. So let's go into our more specific parameter estimates within iWaste. We do that by clicking this pencil option, and we'll type in 99% to reflect this estimate that 99% of that space is open space. It's not built infrastructure. Only 1% is the built urban infrastructure. And then by default, iWaste already assigns that of that open space, 60% has vegetation. And within that, again, open space, there's asphalt that makes up 25% and concrete that makes up 15%. So make sure that when you're updating these more refined parameter values, that the vegetation percentage always matches your soil percentage, and that the soil, asphalt, and concrete percentages always add up to 100 as demonstrated or advised in this warning here. And in addition, these are default values of the depths of each of these materials within the open space category. So soil is typically assumed to be 6 inches. That topsoil will always get removed in the simulations, as well as 3 inches of concrete and 3 inches of asphalt. So there we have, all the things that can be modified. And then that's kind of the most sensitive, in my opinion, parameters you want to maybe play around with, since open space generally contributes to the largest amounts of soil vegetation that are generated after a disaster event. And then we have the rest of these numbers that we've computed based on our CDMS approach that was discussed earlier. So again, we'll hit generate estimates, and then that leads us down to, what do we have here? Our total graphical summary by the building type right here, building occupancy class. And we have the different waste material categories, right? Soil, vegetation, asphalt, concrete, as well as structural building components, and as well as interior components as shown here. So again, pretty useful there. We can display it in either tons or cubic yards, right? We can also download this data and save it as an Excel file for reference in the future. So in addition to the graphical output, we have the tabulated summary here of the waste material quantities. So first we have the open space, again, soil, vegetation, asphalt, concrete, total tonnage, and cubic yards. We can also select these different headings, as I mentioned earlier, to look at some of the default parameters that are hard-coded into iWaste that can't be changed, such as the density of the vegetation or the cubic yard per acre estimate. And we have structural components interior non-structural, again, non-structural building materials, electronics, furniture, other types of waste such as medical waste, maybe from hospitals, and household hazardous waste. So at the bottom, if you scroll all the way down, that's where all the total tonnages and cubic yards are estimated for this individual simulation. So in this case, the total material quantities are on the order of 140 million tons, which seems relatively reasonable given the large aerial extent of this disaster region, combined with the worst case scenario assumption of total destruction assumed by I-waste. So you can see again that the summary looks relatively good. We have maybe 147 miles squared. So again, we'd expect a large amount of soil and vegetation, especially since this is a not very developed area, right? Only 1% is considered urban area as opposed to open area. All right, so now I'll navigate to the treatment and disposal facilities tab as shown here. This one. And we're going to now identify and locate any pre-existing municipal solid waste landfills, as well as recycling recovery centers within the Midland region. I first have to enter in the criteria to filter, as shown in the filter facilities tab here. I have selected, first of all, municipal solid waste landfills. And then I'll also select household hazardous waste collection as another criteria. As shown here, we'll also select metal, C&D, electronics, and composting facilities under recycling recovery facilities. So C&D, we have composting, and we have electronics, and one more, metals. Okay, so since we're dealing with the state of Michigan, again, we'll select Michigan. That may change for your analysis. And we'll say view all facilities. So now I-waste will give us the total number of facilities in Michigan. So orange circles indicate landfills. All of the green boxes indicate the recycling and recovery facilities as populated by the disaster debris recovery tool from US EPA. So now we're going to zoom in on Midland. See, we have about 3 facilities located in maybe a 5-mile radius of influence. So this particular disaster event was relatively severe in terms of the damage to the transportation, road networks, and bridges, for example. So a relatively smaller radius of influence of where we can distribute our waste once collected from the disaster event is relatively smaller. So you can see within that radius, it's about 3 facilities. So we have a potential household hazardous waste collection facility. We have metals recycling facility located near the landfill. You can't see the landfill, it's underneath this box here. And then you also have the composting facilities. So again, maybe located in a nearby location, we can take some of that woody debris, vegetative and soil waste to that compost facility as a potential avenue for sustainable management. All right, so, and you can actually also download the facility list to Excel. That list will give you the address of the facility, contact number, phone number, as well as a source ID recognition number. So you can take that source ID number and then further use the disaster debris recovery tool to obtain more information, such as the GPS coordinates of that location. You can also get some other classification information in terms of what wastes are accepted. And to locate the capacity for these different types of facilities, you can contact them directly, or you can actually look at some additional data sources. For example, for landfills, for example, US EPA's landfill methane outreach program has a great Excel spreadsheet of current waste capacity and waste in place data for a lot of these landfill sites that might be accepting some of the solid waste generated from these events. So that's an overview of the second interface, the treatment and disposal facilities tab. And finally, I'll show some of the benefits of the guidance and information tab available within iWaste. I always like to start with the browsing tab. So you can see here, here's the browse resource tab. And that provides specific search results for any type of event or topic of interest. So let's try browsing through available documents and reports for natural disasters and waste disposal regulations. So we'll go to natural disasters and we'll go to disposal regulations. So now you can see here, the search brings up some important regulations concerning California and federal minimum standards for solid waste handling and disposal, which might be useful for understanding the specific requirements for most conventional management systems for post-disaster waste materials. We can also look up the guidance documents regarding C&D waste materials if we go back here in our search and go to guidance, then go to natural disasters, select construction and demolition waste. Notice we also have other types of things we can select, like landfills or laboratories, and we'll select C&D waste. And notice again, we have multiple things to look at here in terms of citing a C&D management facility or burning of C&D, disposal of C&D waste. But one of the things I found most helpful is comparing the best management practices for what you see and debris materials. As you can see, we have the management techniques in this column, as well as the feasibility in terms of cost, debris reduction, environmental friendliness, human health impacts. So you can see and compare various approaches for which one might be best for sustainably managing a lot of these materials. So that's kind of an overview of the information available under the guidance and information tab, the third interface for iWaste.
In this preliminary virtual training module, a refined approach to apply US EPA's iWaste was introduced to reliably estimate waste material quantity and composition. As informed by HAZUS MH, this approach has been developed to facilitate data standardization regarding the virtual assessment reports and to overcome inherent critical limitations with iWaste in terms of disaster specificity and potential overestimation of material quantities. We have also highlighted some important additional capabilities available within iWaste for locating sustainable material management facilities and researching important waste management policies and regulations. So that concludes our virtual training module for today. Thank you for joining our presentation. We welcome any and all feedback for improvement. If you have a specific question, please be sure to contact our organization via one of the options below. I've also included my personal email account for reference in case you would like to reach out to me personally. Thank you again.